Imagine a heavy block resting on a table, attached to a coiled steel spring anchored to a wall. In this equilibrium state, it sits perfectly still, with no internal or external forces acting upon the system. Now, we apply an external force. We pull the block away from the wall, and the metal coils stretch, physically resisting the movement. That physical resistance is internal tension. By stretching the spring, we are banking our physical effort into those coils as stored potential for future motion. The moment we let go, that stored tension converts into rapid kinetic motion. The block accelerates, cashing out the energy we just invested. This basic cycle suggests a hidden mathematical accounting system. Our physical effort isn't lost when the spring stretches. It simply shifts into a different form, waiting to be used. We define this interaction through Hooke's law. It states that the spring's restoring force, the pull that tries to snap it back, is always negative relative to the direction we pull the block. Pull it right, and the spring pulls left. Every spring has a specific spring constant, or K value. This is the quantitative measure of its stiffness. A thick industrial spring has a high K value because it offers far more resistance than a thin toy spring. This graph plots that restoring force against the distance the block is stretched. The result is a straight line, which shows that the spring's behavior is predictable and linear. The slope of this line represents the constant rate at which the force increases. For every extra centimeter of stretch, the spring fights back with a specific proportional increase in resistance. The force isn't random, it's a precise linear resistance. The further you push the mass from its rest state, the harder the system works to return to equilibrium. In physics, the work done on an object is the product of the force applied and the displacement it covers. Since the spring's force changes as it stretches, we have to look at the cumulative effect. We can visualize this total work as the geometric area trapped under our force displacement line. To find that area, we use the standard formula for a triangle: 1/2 the base times the height. Our base is the displacement, and our height is the final restoring force. When you multiply those together, you derive the formula for elastic potential energy: 1/2 K times the square of the displacement. This is the mathematical proof of exactly how much energy is banked in those coils. This proves that potential energy in a spring is a literal geometric representation of the total physical work performed to stretch it. The spring is what physicists call a conservative force. This means the work done by the force depends only on the starting and ending points of the motion, not the specific path taken to get there. If we trace the block moving from its rest state to a full stretch and then back to the start, we see a perfect balance. The positive work of one direction is canceled out by the negative work of the return. The net work for this entire cyclic journey sums to exactly 0. No energy is leaked or lost to the environment during the round trip. This path independence is a mandatory mathematical requirement. Without it, we wouldn't be able to define a stable potential energy function for the system. Because the spring force is conservative, it acts as a perfect battery. It returns every single joule, the standard unit of work, it consumes during a stretch. If we release the block on a frictionless plane, it begins to oscillate, sliding back and forth in a continuous rhythm. This graph plots the shifting energy states. The U-shaped curve represents potential energy. It reaches its peak at the exact moments the block stops at its maximum extension. The inverted curve is kinetic energy, the energy of motion. It peaks when the block is moving fastest through the center, exactly where the potential energy drops to 0. At the points where these two lines cross, the moving block contains equal amounts of kinetic and potential energy. This horizontal line represents the total mechanical energy of the system. Even as the two curves fluctuate, the sum of kinetic and potential energy never changes. The block stops, starts, and accelerates, trading speed for tension in a continuous exchange. But while these individual states are constantly shifting, the total mechanical energy of the system remains a constant, unchanging value.